Welcome to this explainer. Okay, today we are decoding the invisible architecture that literally makes the entire modern internet possible. If you've ever wondered how cloud networking actually functions under the hood, well, you're in the exact right place. We're going to demystify the internet's blueprint, the 5-layer TCP/IP stack.
Now think about this for just a second. How does data actually cross a network? I mean, when you click a button, send a message, or load a web page, how does that simple little action on your screen seamlessly translate into physical data moving across the globe and then arriving instantly at its exact destination? It feels like magic, right? But it's actually incredibly precise, layered engineering.
So here's our roadmap for today. We'll start with the blueprint, then look at the application and transport layers, move on to the network layer, dive into the data link and physical layers, and finally wrap up with the power of modularity, a top-down journey from your screen straight to the physical cables.
All right, Section 1, the blueprint, understanding the protocol suite.
Before we really get into the weeds, we've got to understand the overarching conceptual framework here. The TCP/IP stack, also known as the Internet Protocol Suite, is basically the foundational blueprint for all modern internet communication. As you can see, it's made up of 5 distinct layers: application, transport, network, data link, and physical. I want you to think of this like a giant data waterfall. When you send a message, your data flows downward, step by step through each of these layers, getting packaged up and prepped for its journey. And then, on the receiving end, that same data travels right back up the waterfall to be unpacked. Let's see exactly how that happens.
Moving right into Section 2, application and transport layers, the user interface and connection.
So this is exactly where your data starts its journey, right at the top of the waterfall, interacting directly with the software you use every single day. Up at the very top, we've got the application layer. This one is responsible for end-user services, providing a platform-independent interface to encode and format data. Basically, it processes the data for presentation to you long before it ever leaves your device.
And honestly, you might not even realize it, but you're using the protocols that live at this layer constantly. We're talking about HTTP and HTTPS for your web browsing, FTP for moving files around, SMTP, POP3, and IMAP for handling all of your emails. Plus, you've got things like DNS, SNMP, Telnet, and SSH. These are the familiar, everyday workhorses powering the interface you actually see and interact with.
Okay, so once the application layer has your data all nicely formatted, it hands it straight down to the transport layer. Now, this layer ensures end-to-end communication. It establishes and terminates connections, and most importantly, it splits that data into smaller, manageable units for transmission. Essentially, it takes that big chunk of formatted application data, chops it up into easily digestible pieces, and manages the actual connection between your device and wherever that data is heading.
Now, what's really fascinating here is the stark contrast between the 2 main protocols operating at this layer. You have TCP, which provides reliable, connection-oriented communication. It is meticulously double-checking every single packet to make sure it arrived. UDP, on the other hand, is connectionless. It just fires off data without checking if it actually got there. That makes it blazing fast, which is absolutely perfect for things like live video streaming. But TCP, well, that is exactly what you want for something like a secure bank transfer.
Section 3, the network layer, the routing engine.
All right, your data has been formatted and chopped into blocks. Now, it needs to leave your application's domain and find a path out into the wider world. Enter the network layer. This layer is responsible for routing these newly created packets across different networks and figuring out the absolute best path based on the destination address. It handles logical addressing, specifically your IP addresses. You can think of it as the GPS system of the entire protocol stack, constantly calculating the most efficient route to navigate the incredibly complex maze that is the internet.
And to make all that complex navigation happen, we rely heavily on IP, or Internet Protocol, for the actual addressing and routing capabilities. But equally important here is ICMP. While IP finds the way, ICMP steps in as the crucial diagnostic tool for network diagnostics and error reporting. If a router goes down or a packet gets lost somewhere along the way, ICMP is that trusty messenger that reports back about the roadblock.
Let's move on to Section 4, data link and physical layers, the hardware connection.
We have officially reached the bottom of our data waterfall, which is where those logical, software-based rules finally meet actual physical hardware. First up in this duo is the data link layer. This layer handles reliable data transmission within a local network, manages physical addressing, which you probably know as MAC addresses, and organizes the data into frames.
So the key takeaway here is that while the network layer gets your data to the right general neighborhood globally, the data link layer ensures local delivery right to your specific device. It manages access to the physical medium and performs some vital error detection right before the data is actually transmitted.
And for sure you're familiar with the protocols operating at this level. Ethernet and Wi-Fi are obviously the huge ones here, along with PPP and HDLC. These protocols are actively working right now to reliably link your smartphone, your tablet, or your laptop directly to your local router. Finally, we hit rock bottom, and in this case, that is a very good thing. The physical layer. This layer specifies the physical medium characteristics and actually transmits raw bits over cables, frequencies, or voltage levels. This is the absolute bottom layer, the literal translation of all our digital ones and zeros into raw electrical pulses, radio waves, or even flashes of light.
The standards down here govern the tangible hardware you can actually touch or physically measure. We're talking about Ethernet and Wi-Fi physical standards, fiber optic cables, and DSL lines carrying those raw bits. A quick fun fact, fiber optic cables transmit data using light pulses that travel at roughly 70% the speed of light. It's literally the physical wire plugged into the wall or the actual radio frequencies beaming through the air right to your device.
Section 5. The power of modularity. The big picture. We've been looking really closely at the granular details, but now let's zoom out and see how this all brilliantly builds together. To summarize our 5 layers, the application layer handles end-user formatting, transport establishes those end-to-end connections and splits the data, the network layer routes the packets via IP, the data link layer handles local MAC addressing and framing, and the physical layer transmits the raw bits via hardware. Notice how elegantly each one hands off its specific duties to the layer directly below it. It's a system that operates perfectly, interacting through very well-defined interfaces.
And that right there brings us to the true genius of this design. This modularity allows for interoperability and for implementing brand new technologies without affecting the entire stack. Because these layers are totally distinct and have those well-defined handoffs, engineers can upgrade the physical hardware, like say rolling out a much faster fiber optic network, without needing to rewrite any of the software rules up at the application layer. It's the exact reason why we can upgrade network hardware or software completely independently without breaking the entire internet.
We're going to wrap up today with this simple but really profound realization. The TCP IP protocol suite is the true foundation of the internet. Every single time you send a text or stream a movie, this exact 5-layer process happens seamlessly in a matter of milliseconds. So the next time you connect, maybe ask yourself, if an architecture this complex is required just to load a web page, what other invisible, highly engineered blueprints are secretly governing the digital world all around us? Thanks for joining me on this explainer.